We've been discussing semantics, and we will discuss the semantics of one final construct in our C++ like language, and that is function call dispatch. So what does a function call look like in our language? Well, let's assume for a general case that it could be a member function. So you specify the class on which the class object on which the function is called, and so that object itself is specified using some expression e0 dot f, which is the name of the function, and then all the arguments specified by expressions e1 e2 dot en. And so this function needs to be implemented, and the question is, so we already seen ways of generating code for such a function called dispatch. The question is, what should be the abstract semantics of such a function call such that they capture exactly what is supposed to be done and only what is supposed to be done and nothing extra. So we want to keep it as abstract as possible. All right. So here's what needs to be done. You need to evaluate the arguments e1 dot en in that order. All right. So the order also matters because each of these expression evaluations can have side effects. Recall that we said that in our language we are assuming that almost all the processing that we discussed is from left to right, but maybe in a language like C or C++, the order may be different, or actually in C++, the order is unspecified, but that's an aside. Then E0 is the target object on which this member function is being called. Okay, if it was not a member function, then that just becomes a degenerate case of this discussion, and so we'll just discuss the more interesting case, which is when it is a member function. And let x be the dynamic type of the target object, right? So let x be the dynamic type of the target object. Recall that dynamic type is the type at the time of runtime, and it may be different for different executions of the same piece of code because it depends on the runtime values and runtime types. And based on that, determine f, which should have n arguments. Now recall that we said because of polymorphism, it's possible that the same name has multiple definitions with different number of arguments or different types of arguments. So when you determine f, you need to worry about that. Also, when you determine f, you need to worry about whether it is a virtual function or whether it is a non-virtual function. So recall that a virtual function has dynamic dispatch, whereas a non-virtual function has static dispatch. And both have different semantics because in the case of dynamic dispatch, the dynamic type is used to identify the implementation that needs to be used. In the case of static dispatch, it is the static type that is used to implement to identify which function needs to be called. So I'm not going to discuss how f is getting determined in my semantics. We're just going to assume that the semantics for determining f are specified elsewhere. So we are not discussing those semantic rules, although we'll need to specify those semantic rules formally as well. But we are not doing that in this exercise. But whatever it is either a dynamically dispatched function or a statically dispatched function. The only difference is which f it is, and that is just kind of encapsulated in these words, determine f. All right, so that's it, and we don't really talk about how we determine f and all that. That would be a different set of rules. Okay, and once you have determined f, you need to actually implement the dispatch. So how do you do that? You create n new locations in the store, and you create a variable environment that maps f's formal arguments to these locations, right? So you just create a new environment in which this function call is going to get executed, and then because of static scoping, we need to create a new variable environment because it's a new scope. The variables that are available are totally different. In particular, the formal arguments of the callee function are available in the environment, and also you need to create new locations to store the actual arguments, and those locations need to be mapped through the variable environment. This is something that we have already seen. And initialize these locations with the actual arguments, which are the arguments at the caller side, the values of the computed by e1 e2 dot en. And finally, set this to the target object and evaluate f's body. All right, so just change the self object, the this object, which is s0, to whatever is computed through e0, and then you have the new environment through the new environment, and you have the new environment, the updated store, and the new object. And under this new environment, in the context, we want to evaluate the body of f. Okay. So before we can start, let's represent f by its containing class x, its arguments x1 dot dot xn. So when I say determine f is not just a name but a definition. And what all does definition entail? It entails the class in which it has been defined. So let's say x. It entails all the formal arguments x1 dot dot xn, which are the names of the arguments given at the declaration of the function. And then it has the body of the function, which is e body. All right. And okay, so that's good. And so we're going to represent this as implementation of x comma f equals x1 dot dot xn and e body. So all the formal arguments and the body. And the body, recall, is just an expression in our language. And so that's how we're going to represent this. And we're going to use this kind of representation in our semantic rules, which we're going to discuss next. All right, so we want to basically have a rule which basically assigns a value or evaluates the value of this expression e0 dot f applied to e1 dot dot en. And also we want to determine what are the side effects on the store because of this evaluation under a context S0 ES, as we have been doing all along. So we already discussed the informal things that need to be done. Recall that the first thing needs to be done is evaluate E0, E1, E2, En. And so we're going to do that. So we first evaluate, let's say, E1, E2, En. And we evaluate it in the order. And the order is encoded by the fact that, the side effects of E1 in S1 are used while evaluating E2 and so on, right? So there is a dependency here, right, from S1 from evaluation of E1 to E2. So E2 can be only evaluated after E1 has been evaluated and so on. Okay. And then we also evaluate E0. So in these semantics, for example, we're going to say that all the arguments are evaluated first and then the target object is evaluated. Okay. So for some reason we have decided that E0 will be evaluated at the very end. We could have chosen a different order. It's just a matter of choice of semantics. But notice that these are subtle things that we sometimes may ignore, but these are very important, right? Because Sn is used in the as context while evaluating E0, and this is important. Okay, and then we say, okay, let V0 be a class object of class X with attributes A1 equals L1 dot dot AN equals Ln, and let f be a function in X such that its formal arguments are x1 dot dot xn and it has a body e body. Then we are going to allocate new locations for this dispatch function called dispatch, and these locations are going to correspond to the formal arguments of the function. So we say lx1 equals new lock sn plus 1. So sn plus 1 is the store that has been that contains the side effects of evaluating all the expressions e1 dot dot en and e0. And so new log Sn plus 1 and Lx2 is new log Sn plus 1 union Lx1 and so on. So this whole block here is basically saying that allocate n new locations such that they are all mutually distinct and they're also distinct from the locations that are already mapped in Sn plus 1. Okay, and finally we also create a new environment which uses static scoping rules. So for example, A1, which is the first formal argument, maps to L1 in this environment. A2 maps to L2. An maps to Ln. And also, we basically say, okay, so this is alright, so A1, A2, An are basically the attributes of the class, right? So when we are executing the member function, one of the things in our language is that the member function may refer to the member fields of the class. So the first thing that the environment needs to have are all the attribute to location mappings for that particular this object, right? And so A1 to L1, A2 to L2, An to Ln, these are just the attributes of the class. And then we say that let's also change this such that x1 now maps to Lx1, the newly allocated location, x2 maps to Lx2, and so on, xn maps to Lxn. What are x1, x2, xn? x1, x2, xn are the formal argument names, right? Because recall that implementation of xf is x1, x2, xn and e body. So x1, x2, xn are just the formal argument names coming from the implementation of x, and that's what x1 is. And what do we want to replace them, map them to for E prime, we want to map them to LX1, LX2, LXN. What are LX1, LX2? Newly allocated locations. Also notice that this choice of actually, doing this syntax of, using, just first mapping all the attributes and then mapping all the arguments. There is a significance to doing this. The other option could have been I just kind of in the same way just kind of say AN, LN and then X1, LX1 and so on in a single array. But the problem with that is that it's possible that the name of a formal argument aliases or X1 can have the same name as A1 or A2 or AN, whatever, right? And so we want to say that if they have the same name, then which one should get precedence? And in this we are clearly saying that the X's, like the X1, X2, X's should get precedence if they have the same name. So if there's a name conflict, just like in static scoping, we say the innermost scope wins. Here also it's the innermost scope, which is the names of the formal arguments that win. And that's the significance of writing it like this. And also we need to create a new store, because in the new store we are going to actually map these newly allocated locations LX1, LX2, LXN to the actual argument values, which were V1, V2 and Vn. So we say Sn plus 1 modified such that V1 is LX1 is mapped to V1, LXN is mapped to Vn. And that gives us a store Sn plus 2. And now we have E prime and Sn plus 2, and these are the environment and the store under which the body should get evaluated. The only thing is we need to also change this object, and so this is the final part of our rule. V0, which is what was evaluated through E0, is the value of this object. E prime, which is the new environment, Sn plus 2, the updated store, evaluate E body, and let's say it evaluates to V comma Sn plus 3, then this entire function dispatch also evaluates to V comma Sn plus 3. Our rule is almost complete, except that notice that we allocated new locations using the new lock operator in LX1, LX2, ... LXN. And this these locations are still available in Sn plus 3, and even after the function call dispatch is over, these locations will continue to remain allocated in Sn plus 3. And if you recall from our declaration rule, that amounts to a memory leak, and if we use such semantics, then it burdens the code generator or the compiler because it has to maintain these locations and their contents even long after the function call dispatch has completed. This is not what we want, and so the complete rule in fact involves subtracting these locations LX1, LX2, ... LXN from Sn plus 3. And so this is our final dispatch rule.